you're wondering where Dick was, I guess George was explaining this here for us. He is here now. I do have a couple details I want to start off with. So first of all, there are some people who have not yet registered, so at the break, it's registration and coffee, so it's an inducement. The coffee is in 110, which is just through the doors, 2 sets of glass doors, and then in the room behind the elevator bay. Okay. And also I'm told by Margaret that some people have not yet paid for dinner. If you haven't, she's going to take your money or your life at coffee. Okay. So I just say a few words to people who weren't here for the CITA 25 part. We did have a huge turnout, about 180 people registered, probably a little over 200 were here. Okay. And there are of order 60 or 70 former CITA postdoctoral fellows. And I tell you this because it's clear that people, while they were here, did a great job on science and were very productive, but they also enjoyed themselves. And one of the reasons for that, of course, was that Dick was at CITA. Dick and Scott, I should say, really set the tone. I mean, we've always had great science coming out of CITA. That's a legacy of theirs. Another one is, of course, that people like to have a good time. And Dick certainly embodies that. He's also a bit obsessive at times, as you may have noticed. He gets a little worried about details sometimes, which are not necessarily that important. I'm not quite sure why he was really late this morning, but I suspect he was running around in panic. Okay. But you could have left early. Okay. So one of the things that I recall very well, I'm not quite sure who started it. It may have been actually Dick. But Dick has been running Cosmo Beer for more than a decade, maybe 20 years. That's certainly one of the things that people at CITA remember well. Just wait a minute. Somebody's not happy in the audience. You notice though John is also late. This is probably a learned behavior. Anyway, just I can point out that my actions do speak louder than words. I can tell you that Dick has created a great atmosphere in CITA over the last 25 years, along with Scott, of course. But actions do speak louder than words, and the fact that so many CITA postdocs come back really does tell you that people enjoyed their stay here. Okay. Well, since we're starting late, I think I'll just stop there. Oh, I will say one other thing, of course. Besides Cosmo Beer, Dick's also very famous for his love of wine. And that may be, of course, why some of you came here. You're aware that he probably took some care in selecting the wine tonight. And we'll see how well he did. But I can tell he did put a lot of effort in. So with that, I'll turn it over. Peter is chairing the session. And he can, well, actually, George, may as well just get up and start.
Well, I wasn't joking. It really is a lander, Dick, and I'm not going to let you go until you admit it. If, like me, you try to find the program and Google Bondfest, you've got something like this. Unlike one of my postdocs who Googled Dickfest, you get a very different. Of course, I'm a great fan of Dick. I regard Dick as my closest collaborator. And what I'm going to talk about some of the stuff that we did. We wrote 15 papers together. We started in 1980. And here they are, ordered by a number of citations. And as I said to Carlos many years ago, if you want to get citations, it's not the intellectual quality of the paper that matters, it's whether it's useful. Find some fitting function or something. So I'm not going to talk about this. So what I'll do is I'll start from the very first paper we did, pick some things. We started in 1980, and the last paper that we wrote together was in 1999. And even with close collaborations, after a while, we went up with departments to run. Dick has his citizens, I have my cavaliers, and you have families and so on, and so naturally collaborations wane. But while we were working together, it was great fun. This was what Dick was like when I first met him in 1979, and we met at Berkeley. We were both postdocs there, and that's when we started collaborating. So isn't that cute? The last time there was such a close Dick-George collaboration led to a war in Iran. So we collaborated so closely that we used to sit at separate desks and derive stuff and then compare results to make sure that we got them right. It wasn't just all work, there were trips and things. This is Ray Carr. And so we had lots of fun as well, including the infamous trip to Paris, of which we never speak. Don't you dare say. And since there are so many friends from those days in the audience, I decided to put this picture in. Dick's not here, but this is from a few years later when we were doing the cold dark matter simulations. This is Mark Davis. There's Simon. He's now dyeing his hair. Carlos, who has actually lost weight. And for some reason, this is quite a typical picture. Joe was always lurking somewhere. So, this was the first paper that we wrote together. And this arose, Dick was working on supernovae at Berkeley. And I was talking to Mark Davis over the phone. And he said, have you heard about this result? It's a reporting measurement of a 48 electron volt neutrino. I said, no. So I walked into Dick's office and said, do you know anything about this? And he said, no, but I'll make some phone calls and find out. So he got the background of the Russian experiment. And so we started thinking about, what this would mean for structure formation. And this was the result. Of course, what we calculated was the characteristic scale for free streaming of neutrinos of a given mass. And
so 30 would be 1,000.
In people's notation. this is our notation. You can maybe use my train. Okay, we argued so much about this picture. Okay? We calculated the characteristic scale, and I wanted to write it from a negative point of view, that this didn't match observations. It would mean that the scale of structure would be too large, galaxies would have to form from pancakes and so on. And I wanted to write it from a very negative point of view. Dick, was more sensible and decided that we should just present it in a fairly neutral way, which is what we did. But we worried a lot about this stuff, and we also so we didn't just look at adiabatic perturbations. We also considered isocurvature, dark matter perturbations, and we also thought about what would happen if you had heavy particles, heavy nuclear interacting particles, and that was a way to bring this mass scale down. So there's actually quite a lot of stuff in that paper. And of course now we know that neutrinos really do have a mass, and this shows you the various possibilities from atmospheric neutrino and solar neutrino experiments with normal hierarchy, inverted hierarchy, and of course if the absolute mass of neutrino is high, then they're degenerate. So So the picture that you get is there should be a detectable neutrino mass. There should be a neutrino mass of around 0.06 eV or greater. And the best way of proving that sort of mass range is cosmology. And this is a figure from a paper combining WMAP and not the CMB results with baryon oscillations and measurements of the Hubble constant. And you can see that the different data sets give you some upper limit of around 0.2, 0.3, or somewhere in that region, electron phase. And as Wendy said in the very first talk at this meeting, that if you can improve the precision of H0, for example, then you will tighten this construct. So, this is, I mean, it's interesting, we did that work on neutrinos. I think that was the first time that in the Western literature, at least, the link between the nature of a particle and structure formation was first discussed. And cosmology still seems to be the best prospect for constraining or possibly detecting neutrinos. So, in the late 80s, early 90s, I was working on structure formation, and this shows the AKM survey that we did at the time. We did various redshift surveys based on IRAS and so on. And this shows the angular correlation function, a CDM model with lambda equals 0, and a CDM model with a cosmological constant. And that was my favourite explanation of the data at the time. And I was invited to go to Downing Street and discuss this, present a talk on this stuff to Margaret Thatcher in 1990. And I showed this stuff and gave this explanation. And a few weeks later, Margaret Thatcher resigned. This was such a horrible she couldn't possibly carry on this. So Mrs. Thatcher was not the only person that was unimpressed by this. Okay? Dick said, come on, there are many ways of explaining excess large-scale structure. And so with Jim Bardeen, we co-wrote this paper with a typical Dick table. Here's the lambda CDM model with lambda equals 0 and various measures of large-scale structure, correlation functions, velocity, bulk flows, temperature anisotropies, which hadn't been measured at that time. This is the lambda CDM model. And there are many others, isocurvature cold dark matter combinations, hot and cold, mixed dark matter models. Do you remember what these models do? You do. There's even CDM. So this is CDM with a decaying particle, decaying heavy particle. This is CDM plus X, and the X was just a bump in the spectrum to explain large-scale structure, and the referee allowed this. So it shows you, Dick's imaginative powers. But I'm saying to Dick, it is this. This paper, I think, is responsible for holding back the field by at least 6 or 7 years. Anyway, I think the most, from my point of view, the most satisfying, significant paper that we wrote together was this one, where we set ourselves the goals of calculating fluctuations in the CMB as accurately as we could, valid on all angle scales for adiabatic and isocurvature models. And these are some of the results. The acoustic peaks temperature and polarization as a function of wave number and then projected onto multiple lights on the sky. And in this paper, we did a very simple thing of constructing images on the sky. And so this was a realization of an adiabatic cold-up matter model in a 10 by 10 degree patch of the sky. And nowadays nobody bats an eye at these kinds of, we use them all the time. But at the time, when I gave talks and referred to, said it was a simulation of the CMB, people didn't know what I was talking about. They were sort of confusing it with n-body simulations. And so I was, had to explain very carefully that it was a Gaussian field generated from a power spectrum that we computed. So when we did this stuff back then, did you ever think that we would see images of the CMB like that? There you go. I wasn't so sure. It's remarkable that that this stuff has been detected. We also computed the polarization pattern, and we got this wrong. Okay, so that was a realization of the polarization pattern on the sky. And what we've missed, for some reason, we've missed the correlations between temperature and even polarization. And we just weren't thinking, we was really focused on the temperature analysis, and we didn't think carefully about the polarization pattern. But we knew anyway. So, remarkably, that's what we now see. So all of this stuff is observed to high precision, and it fits the simple adiabatic model with a mini-scale spectrum. So, remarkable progress we have learned over the last 25 years or so, but we don't understand 96% of the universe. So there's plenty more to do in cosmology, and after, more or less after, we did that sort of work, we got involved in the Planck proposal, which started off in 1992. This is a picture of COBRAS. Planck was the merger of two proposals, COBRAS and Samba, and they were proposed in 1992. Planck was selected in 1996, and it was launched a year ago. Yesterday was the first anniversary of Planck's launch. So it was 16, 17 years from proposal to launch. And during this period, our collaborative papers were basically on prospects for determining cosmological parameters for Planck, and they were related to the Planck sample. So Planck was launched. Dick and I went to the launch. So this shows Ariane 5, and inside the fairing there's the Herschel infrared telescope, and Planck bolted on underneath. And this shows the launch of Planck from the distance that we were at. And the third picture shows, I'd never seen them. I wasn't prepared for what happened. if you ever get an opportunity to go to launch, take it, because it's really unlike seeing it, on a computer screen. It's just this amazing explosion, and off it goes. And then from where we were standing, it went up, and then sort of turned down. this is an optical illusion, but I wasn't prepared for it. So it started to go down. And then, at around this point, it ejected these boosters. And once it ejected the boosters, there was this kind of little crackle and pop, and it was gone. I turned around to Dick and I just said, "Oh, that's that." What have we just seen? And I don't think Dick was too sure either. He didn't seem confident. So we went off to the monitors to see what was going on, and the rocket was absolutely bang on the right trajectory. So we were happy. So here we are, just after launch, and inflation was discovered in the 1980s, and both Dick and I duly inflated. And this is me on the phone to Cambridge, where they broadcast the launch in the lecture theatre there, saying, "It's okay, it's okay." And they said, "We know it's okay." What did you think had happened? So anyway, this is a terrific. I think this is a terrific shot because 27 minutes after the launch, Planck and Herschel separated, and this shows pictures from a camera on Herschel, and it shows Planck in its carbon fibre cylinder. This is Africa in the background, and at that point, Planck was detached. The cylinder was ejected. Planck was spun up, and that was it. And it was off to L2. And at the time that Planck was injected into its orbit, the velocity of the injection was accurate to a fraction of a percent, which is incredibly impressive, and they regularly achieve that kind of precision. Once Planck was on its way, it was amazing. Some of the scientists, the people that had worked on the instrument, actually burst into tears. So, very emotionally intense experience. So, what is Planck designed to do? Here are simulations of what we expect, what we expected from Planck at the different frequencies, running from 30 to, in this plot, from 30 gigahertz to 340 gigahertz. That's with the noise subtracted. And what I think I can say, Francois will shut me up, is the real data look very, very similar to this. I'm not going to show any real data, but Francois will show some real data. It's amazing that complicated software is working flawlessly. So after the coding results were announced, Dick, Simon, and I wrote a little paper on interpreting coding. This shows a letter that I wrote to Martin, Simon, and Dick, because Martin had said, "What about gravity waves?" And so what I did in this letter was just look at the tensor scalar ratio for parallel potentials, and the conclusion was that unless the potential was incredibly steep, gravity waves were a small component. And we should have just published that, more or less as it was. But within a year, we'd done a very detailed calculation of the tensor nodes. And again, we were so focused on temperature that we calculated the polarization pattern, but didn't project it onto the scope. just didn't project onto the star. So we missed the E and V decoms of these, which of course are now a major goal for CMB experiments. So let me just show you some simulations of what we think Planck do. So here are QU maps on the sky. So this is degraded to 10-degree resolution, and with a sky cut imposed. So that's theory. And that's what we think we can extract from Planck. But we'd like to isolate the B mode. That's what we think we can do with 2 sky surveys. And Planck has been approved for mission extension, so we should get these 5 sky surveys from Planck, as long as it keeps working. And that's what we think we can do with 4 sky surveys. So compared to theory, that's for a tensor scale ratio of 0.1. So Planck has the sensitivity to do well. What we don't know yet is whether we can control the low frequency noise properties and polarization systematics to be able to do this. Okay, so that is at the edge of what Planck would do. Planck intrinsically has the sensitivity, and I'm also firmly convinced that the polarized foregrounds control. But if Planck doesn't succeed in doing this kind of science, Vic is lucky enough to have a second shot with Spider. So Dick's in a very fortunate position. So Dick has introduced some vocabulary that we regularly use. I think he was the first to introduce cold, warm, hot, dark matter into the cosmic lexicon, the cosmic web. A lot of the notation that is commonly used came from Dick, and people have me to thank for removing some of the superscripts and subscripts. There's gastrophysics, and when we were writing one of the Planck papers, I wanted to call it something like prospects for determining cosmological parameters with the proposed Planck satellite, assuming that it launches satisfactorily in instruments, or something like that. And Dick said, let's just call it forecasting parameters from Planck. And I said, forecasting? That's horrible. And anyway, Dick won that battle, and forecasting has become part of the language, and I'm very glad that it has, because now if I see a paper on AstroPH which has forecasting in the title, I know not to read it. That's a really useful contribution to the field. But the phrase that I most associate with Dick is this. That's quite a typical Dick reaction while we were collaborating. So here went through the ABS, and this shows Dick's publication record. So it's plotted year by year in silk units. Okay? And a silk unit is 10 papers per year. I introduced this unit for Joe's 60. You can see that, and in Dick's case, in Joe's case, his publication record varies between around 1 and 2.5 silk units. And curiously, it anti-correlates with the solar cycle. But I will let Glenn Starkman interpret. So, anyway, you can see Dick has seeded the silk unit once. He got very close the second time. But the interesting thing is that the overall trend is upwards. So we can expect more from Dick. Now, I said that our last paper was in 1999, and that's not true. Strictly true. This one has been accepted for publication. It's the first paper that we've written together since then. And there is me. You can see, I mean, it's an indication of how our subject has changed over the last 30 years. We have, just this massive audience. The research is very different now than it was back then. But we, the BE collaboration is set to continue. So the bondage really does carry on. So, anyway, I've given a summary of some of the things that we've done, some of the impact that it's had. As I said at the beginning, I regard Dick as my closest classmate. It's not just the science, but it's the human bond that is important. And long may it continue. So happy birthday, Dick.
Questions, comments?
What happened in Paris?
Totally classified. At which time?
Well, it's a great pleasure to talk at this very special meeting. I think most people know today actually is the big day. This is Bond's actual birthday. So it's really special, and I'm delighted to be able to I'm going to talk about the subject which I worked on with Dick and some collaborators for about 10 years in the 1980s, these very massive stars, which have had a rather checkered history. They've gone up and down in popularity, hence the name, the title, The Rise and Fall, and Rise Again, the Very Massive Stars. But right now, they're really popular. I have to say that there's a subtitle here, The Rise and Fall and Rise Again of Dick I first met Dick when I went to Caltech in 1975. I was doing my PhD with Stephen Hawking, who was there that year as a Lincoln Fellow, and a Fairchild Scholar. And I met Dick, who was doing his PhD with Willie Fowler on stars. We became great buddies, and my most vivid memories were on Friday evening when we used to go and TGIF and have drinks in the bar. And then we went back to the mansion, which was the house where Dick lived. Some very interesting friends. And we used to have wonderful time there on Friday evenings. Very, very deep thoughts. And we had most amazing was Dick's thesis, which was on, as I'm sure most of you know, it was on stars, neutrino productions and transport during gravitational collapse. That's an actual photograph of his thesis, so you can see how thick it is. So in those days he was working on stars. He got his PhD. There's a picture of young Dick, the first, obviously, step of his rise, getting his PhD. Only the clothes had changed. And there is Dick with Willie Fowler and his wife, sorry, Willie's wife, Artie Fowler. So that was a very special moment. We had lots of fun there. He did go through his rocky phases, and there's a picture. He's working with his, also into Willie Fowler's group. Now, actually, it was a long time before I actually saw Dick again, at least worked with Dick again. We moved to Berkeley. We were both there as postdocs. In my case, really as a result of Joe Silk. And we lived in this house. We called it BBC House because Bond, Bagelman and Carr, we lived there. Back to the pad. And really, it was there was no furniture we could never agree what to buy, but nevertheless we had a lot of great times there, a lot of parties, and I know Mitch will be talking more about those later. It's still there, the house I mean. And it's incidentally, notice 1980, exactly 30 years ago, so this was the midway point in Dick's career so far. Now, here are a few little party pictures. B, Bond, Bagelman, myself. Jean Brodie joined us. She replaced me when I went back to England. Here's a typical party picture. There's Dick in his pensive mode. There's Joe, and incidentally, Joe is so important because of Joe inviting so many of the Brits to Berkeley that we had such a great time, and I think it's such a great scientific introduction tonight. So thanks for that, Joe. That's a picture of me looking. Well, I had more hair there on head and on chin. That's a picture of Dick again. I didn't want to show pictures of me, it looked really cute. Now, there's another picture taken in Berkeley. There's Dick and Steve Hadgett, Mitch Bagelman, George Efsthathiou and George Lake. Notice there's Mitch Bagelman. Notice he's holding hands with a bear. But don't worry, because at one of the parties he met Claire, who he later married. So another great thing that happened at Claire. Now, my own collaboration, George was talking about his collaboration with Dick. My collaboration was mainly in the 80s, and we produced a series of papers mainly to do with these very massive stars. These are the papers in 1984. These were papers really in collaboration with Dane Barnett. Remember, Dick had come from stars. His PhD was on stellar evolution. I come from cosmology, and I think really because of that interaction, Dick got interested in cosmology and I got interested in stars. So for me, it was a very valuable collaboration. Later on, we collaborated with Craig Hogan, and we wrote some papers on the infrared background from these sorts of stars and also other sources. And so that really summarized. We did many other sort of smaller papers, but those to me were it was a great period, and I'm very grateful for Dick and Craig and the audience for a wonderful collaboration. I'll say a little bit about these papers. Now, this paper on the evolution of fate of very massive stars, I'll say a little bit about this. With each paper, there is a sort of, to me, a sort of an iconic figure which summarizes it. This is the figure which, to me, summarizes this great paper. Sorry, I couldn't throw that. Incidentally, it's a bit embarrassing because I'm going to be very praising these papers, but I'm not praising myself, I'm praising Dick. You can always tell a paper Dick done, a figure done by Dick, and one done by me. A paper by Dick has got curves in it. My papers are always straight lines because I sort of do them analytically. I also tell you a little secret about myself and Dick. Of course, one always has little arguments with collaborators. With me and Dick, the biggest arguments were always about commas. Whether we should have commas or full stops. And I was actually, I have to say, Dick, I was really annoyed. I discovered this yesterday. The very first sentence of our paper. Anyway, we'll sort that out afterwards. Now, let me just in case you don't know about VMOs, we call them very massive objects, VMOs. Unfortunately, nowadays they're called very massive stars. Let me just briefly, because I have to put some science into this talk, so let me just briefly explain these properties. A VMO is a star which is bigger than 100 solar masses. And that basically means that it will encounter what we call the electron-positron pair instability during its oxygen burning phase. And so if you look at your different types of stars, everybody knows that the objects less than a solar mass, they tend to leave neutron stars or black hole remnants. The objects bigger than 100,000 solar masses, they're called supermassive objects, and they collapse due to relativistic instabilities. We were interested in what were then very neglected intermediate regime, the VMOs, between 100 and 100,000 solar masses. The physics is pretty straightforward. During oxygen burning, the core temperature goes above a few million degrees. The thermal energy then gets pumped into electron-positron pairs rather than the pressure. That leads to an instability, which means they collapse, and you get a nuclear explosion. And you have two outcomes. Either, if the mass is less than some critical value, it will entirely explode. If the mass is above a critical value, it will collapse to a black hole. And one of the key questions was what was that critical mass? Now this is where I got really excited because I wanted to explain the dark mass, and this was, to me, a wonderful way of putting all the dark mass in the black hole. Because most of my life has been devoted to black holes. I'm obsessed with black holes. And so this was a great way of getting a new population of black holes. Now, one of the big problems of these stars, though, is that if they're bigger than 100 solar masses, they're radiation pressure dominated. That means they're unstable, they pulsate, and then they lose a lot of mass. And it used to be thought that they lose so much mass that they really couldn't exist. And in fact, if you look at our galaxy today, it's clear that such stars are very rare. The biggest star, there are arguments if you look at star clusters, for example, that you can't have stars bigger than 150 solar masses. And in fact, that's what you would expect, because the stars forming today, you expect them to have a mass function peaking at about a solar mass because of the effects of cooling, using the G's mass, etc. Now, it's very different though, because the very first stars, the stars that formed in the early universe, they could well have been much more massive because there were no metals. There's no metal with no metal cooling, and therefore there were reasons for believing that these stars might have formed. Nevertheless, most people didn't believe it. This was a time when they really were not very confident. Nevertheless, VMOs are really useful. From a theoretical perspective, they are so simple. They are essentially n equals 3 polotropes. Their temperatures, they all have a temperature of about 100,000 degrees. They all have the energy luminosity. They all have a lifetime of a few million years. So really, they're far simpler in terms of their evolution and their structure and the sort of stars which we know exist. And what we did in this paper, we discussed using purely analytic models, things such as the helium enrichment, just say, during their mass loss, the dynamical instability during hydrogen shell burning, the effects of apparent stability in alpha quenching, and in particular this crucial mass cut. And purely analytically, we were able to show that the core mass, the critical oxygen core mass, that cut between was about 100 solar masses. And that would correspond to an initial hydrogen mass of about 200 solar masses. But there was a big uncertainty there because you don't really know how much mass loss there is in the receiving phase before it gets to the oxygen core. Now, I should stress that these calculations are essentially analytic. Of course, the real proper numerical calculations were being done by Stan Woodsley and people, but more or less coming to the same conclusion. So it was really quite exciting. Now, then there was the paper on the cosmological consequences. I was very interested in what the remnants of population-free stars would do. I was interested in the fact that the remnants might make dark matter, or gravitational waves, or gravitational lensing. We were also very interested in the radiation production. They might make an infrared background, or even generate the microwave background itself. Not now a very popular idea. They were interested in their explosions, that they might form galaxies, or ionize the universe, or enrich the universe chemically. Well, then nuclear synthesis consequences, there are various problems they might do. They might in principle use helium. So we had a long paper explaining that. I'm afraid all my papers with Dick were very long. Dick has a tendency to write long papers, and so do I. So I'm afraid these were doubly long almost. But I suppose this is the sort of iconic figure from that paper. And these are the regions which are excluded. This is the density of the stars against the critical density units versus their mass. And these are excluded by various reasons, by background light, enrichment, and dynamical effects. But the key message of this diagram was that the one range in which population-free stars explain everything was the VMO range. And so that's really why, I think I was so excited, and I think they were never excited. Nevertheless, few people believed in them. I'm now going to plot the first step of the diagram here. This is the popularity of the VMO scenario. Sometimes called intermediate black holes. Those are the black hole remnants. They're really the critical mass. This is popularity against time. And as we go through my talk, I'm going to show how this rise and fall of popularity. So here we are. I'm not putting units on popularity because I'm not going to define it. But this is the fact. I at least got no problem with me and Dick, I think, because we realised we can make a lot of black holes. And then as time goes on, in my talk, I'm going to talk about how this popularity evolved. We were very interested in gravitational waves. We realised that these black holes would generate a lot of waves, which would be detectable back to very high redshifts. This is redshift against mass, using the various gravitational wave detectors then available. So this is the characteristic period and the amplitude of the wave. We're also very interested in the coalescence if we had binary VMOs, and they would also be detectable. And then this was a rather a cluttered diagram, but we are interested in these, plot the density of the gravitational waves against the period. This is the sort of regime which will be detectable by Peter and LIGO and things like that. But bear in mind, this was 1984, so it was well before this was actually practical. And now, of course, we're in an era where this is actually likely to happen. We will hope to detect, of course, these coalescences, but maybe not from these VMOs. Now, then there was a very exciting development, because in 2003, the Japanese found an infrared background, XS, 2 to 5 microns with a black body temperature, and it was just the sort of background we expected from VMOs if they had a mass between 100 and 100,000 solar masses in something like a critical denser. So we thought, this is it, great, these things exist, we'll be famous. Well, so there was our temporary moment of excitement when we thought these were really there. And this was a meeting in Fermilab in 1984. There's Simon. Esteban died. There's Dick Kaiser, Mark Davis, and Jim Young. And incidentally, but let me break down to go into more personal sides. In 1984, a lot of us in this room were in Santa Barbara, the Institute of Theoretical Physics, and indeed, a lot of this was just before CITA was born. And this was Dick with Nick and Kaiser, his wife. There is again, and there is Simon on the floor. Sorry, Simon, best possible sense. There's a nice picture of Carlos and his wife Sue. And incidentally, I have to say something. I lived with Carlos and Sue in an apartment for 4 months. And it was a wonderful experience. As a result of that, I learned what love really means. And let me explain. You see this? These are oranges. Okay? Well, Sue used to, every morning, she used to squeeze 12 oranges for Carlos's breakfast. And I thought, well, that's true love, and I always said if ever I found someone who would do the same to me. However, I want to point something out. Carlos doesn't seem to have changed, but he has a little bit. You notice he had a moustache in those days. I have to say, I was very sad, Carlos, when you lost your moustache. I feel you became more fragile. However, meanwhile, there was a paper, the next academics research stage was we started collaboration with Dick and with Craig as well, and I think that started in Santa Barbara. And we started looking at the infrared radiation from not just these VMOs, but all sorts of sources. And in particular, we looked at the effects of dust, because one of the key messages was that dust will reprocess any source of radiation if it's far infrared. And I have to say, yesterday, or 2 days ago, I heard the nicest talk I've ever heard by Lloyd Knox. And when I say nice, I mean it was nice to me and Dick and Craig. But in summarising let me just say first of all, the key prediction, one of the, from a VMO point of view, the point was that we realised that there would be an infrared, near-infrared background, a very characteristic frequency and density, which just essentially depended on the redshift at which these VMOs were burning. If there was enough dust to reprocess it, it will get channeled into the far infrared at again a wavelength of 400 microns, which is really very insensitive to all the other various parameters around. And this is a rather complicated diagram of the density of the radiation against the frequency. These were all the observations at the time, and these were the sort of backgrounds predicted from the VMOs and all the various other sources. So it was a sort of trade-off. If there was no dust, all the radiation would be in the near infrared, but if there was dust, a lot of it would get channeled into the far infrared. And so this, we thought, was the key signature. Now, this is a little bit embarrassing. I'm going to quote a few things from Lloyd's talk, because he summarised our paper much better than I could have done. They made dense plots with big long captions. They communicated statistical properties of CIB anisotropy before the invention of CL. The background was indeed detected in COVID data in the 100 to 1,000 micron range. The detection led to further theoretical work, a body of work which we may call collectively. Bear in mind that this, what follows, is not mine. It's the pun of Lloyd. The sons of... I have to say, thought of myself as a father of... So I think it probably, I mean, it's a bit embarrassing talking about this because it's, I was told, but of course this is the, I'm praising great here. So, but I mean, I do think it's probably true that the paper did have quite an influence. The anisotropy was indeed detected by Spitzer and then by Glass and T. Now, let's now go back to the personal side. In 1987, Dick came to stay with me, and I think this is a well-known story, and I'm not going to go into much detail, but let me just say...
Was it in Paris?
No, it wasn't.